Hi, everyone, and welcome to our next lecture on algorithms and data structures. In our last lecture, we finished recursion. In particular, we looked at the master theorem and dynamic programming. And today, we will be looking into sorting. We'll look at various sorting algorithms. We will, in detail, look at two very efficient ones, which are merge sort and quicksort. And those algorithms can be expressed very easily using recursion. So that's where we are actually linking this chapter to the previous chapter. But we will first start with a few simpler sorting algorithms, and then we will also compare their complexity. And after we've looked at these sorting algorithms, we'll wonder at the best sorting. We will wonder if we had the best possible sorting algorithm, which complexity this one would have. So we will look at the lower bound of sorting. Sorting is probably one of the most important problems in computer science, and it has been well studied for many decades with numerous sorting algorithms. And many data sets are often stored in order because then we can search efficiently in the data set, we can manipulate it efficiently, and so forth. For sorting, for searching, you have already seen the binary search algorithm, which relies on a sorted data set. And today I will show you how we can sort a data set. There are also many advanced algorithms that rely on sorting as a subroutine, or we have more advanced data structures that sort that store our data in a sorted way. For example, certain kinds of trees that we will see starting the next lecture. So overall, sorting is super important because we can then work with data much more efficiently. And today we will discuss how we can actually sort data. And once we have done this, at the end of today's lecture, I'll also share some best practices when it comes to Python and if you want to do sorting in Python. I will now switch to my iPad and start visualizing the first sorting algorithm that we are looking at. The algorithm we're discussing now is called bubble sort. And while I'm starting to explain this, maybe you want to share in the chat names of other sorting algorithms you have come across. I have just mentioned a few in the overview of today's chapter, but if you have heard about other sorting algorithms, maybe just share them. Already see some students referring to Radix sort, Bogo sort. Bogo sort is more like a choke, but we'll be looking at that later. Some of you wrote quicksort and merge sort. Yes, I have mentioned them before in the overview, but Radix sort and Bogo sort are probably less common. We'll briefly mention Bogo sort later. So let's start with bubble sort. Bubble sort is one of the simplest sorting algorithms possible. It's not very efficient though, but that doesn't matter for now because we'll just look at its general concept. So we have a data set, say 5, 3, 8, 4, 6. And I want to sort this data set now. And what I'm doing is I'm comparing the first two elements. So 5 and 3. And I want to bring them in order. And 5 is greater than 3. So I flip 3 and 5. So I have just compared the first and the second element. And then I'm comparing the second and the third element, whether I should flip them, and I shouldn't flip them because 5 and 8 are in the right order. So that's fine. Then I'm comparing 8 and 4, and 8 is greater than 4, so I need to flip those two. So 3 and 5 stay from the top row, and then 4 and 8 are flipped. And then I'm comparing the 8 and 6. And I see 8 is greater than 6, so I have to flip them. So 3, 5, 4, 6, 8. This was now one iteration through the data set from left to right, and I brought in a little bit of order, but obviously the data set is not fully sorted yet, so I need to start another iteration of this procedure, and again go through from left to right, compare. Then my 3 and 5 are in right order, but then 5 and 4, so I need to flip them, and so forth. So I keep I keep going through from left to right and change the order. And if there's one iteration where I went through from left to right and I haven't changed the order of any pairs, then I'm done. So that's a super simple algorithm. And we can also wonder how we can implement it together. And I'll show you that this is fairly easy to implement. There is one quick note which we can use later to speed it up. We see after we've done one iteration through the data set, we have actually moved the greatest element 8 to the right, because 8 was somewhere, and then we flipped always 8 with the neighbor when necessary. So in this first iteration, we have moved the greatest element to the right. And we'll now try to implement this. I'll share my session very soon. So we will implement our bubble sort, and we pass a data set, which is called as A for now, just to keep it short. And we assume A for now is a list, for example. And we will need its length. So there are n many elements. And I have this outer loop, which was just this outer loop of the visualization that I go through the data set. And since I have n many elements, in the worst case, I have to do the outer loop n many times. But there's a second loop inside. And this is the loop, which was the inner loop, the one I've visualized, where I go from left to right, and I always flip two pairs if necessary. And then once I have done the one iteration of, or one whole iteration, or once I have finished the inner loop in one iteration of the outer loop, then I will have the inner loop again. And so what we actually need is, we need j in the range of n minus 1. You will soon see why it's n minus 1 and not just n. And we can even optimize this further. So to be optimized, we'll see this in a moment. And I need to check in the inner loop if aj is greater than aj plus 1. So I'm checking if, when I look at a pair of elements, if the left element is greater than the right one, and if so, I need to flip them. And because I have my index j and I add one on top, j can only go from the range of 0 to n minus 1, where n minus 1 is excluded. If I put in n, I would have an invalid index, because then I would look at the last element and try to look after an element behind the last element, which isn't there. And then I can say, well, I'm taking, creating a temporary variable, which is element j. Then I can just put the value from the right into the left element, and then I put in the right element our temporary value. You can do such a flip more efficient or in less code in Python if you wish. There's a way how you could do this without explicitly defining your helper variable, but this is not a Python course, and I still want this to be understandable. And I think in many other languages like Java, for example, you would be creating your helper variable. There's one more thing we can do to optimize, just for a small optimization. But I've said before, when I've had visualized this, once we have done one iteration of the outer loop, so I have once gone through them and flipped these pairs when necessary, I said the rightmost element then is the greatest element. That was this 8 before. So in one iteration, I have moved the largest element to the right. And that's why I don't need to be looking at that element anymore. And if I do one more iteration of the outer loop, I will then have moved the second largest element to the right, which is then the second last element. So once I have finished an iteration of the outer loop and I have run once the inner loop totally, I have always then moved one more element sorted to the right. So I need less and less iterations of the inner loop. So I can actually just say this is n minus I minus 1, because each time I have finished the inner loop and I've so finished one iteration of the outer loop, I have moved one more element to the right that will stay there, and I need to look at less and less elements. It's just a minor optimization. And we can try this out now with our data set from before. We say this was 5, 3, 8, 4, 6. And we pass the reference to our data, and then data is manipulated. So data is not being returned, but we manipulate the parameter. And so we can actually see that it got sorted. So it's 3, 4, 5, 6, 8. So it's so this comment up here to be optimized, I forgot to delete now because we've optimized it. We put in a minus I. Do you have any idea what the O complexity of bubble sort could be? The worst case. And if so, maybe send this to the chat. What do you think? It's O of what? I got a few answers in the chat, which are right. The worst case time complexity of bubble sort is O of n squared, because it's a loop within a loop, and you know all the tools of how to determine the number of, or the order of the number of fundamental operations we are carrying out. So the worst case complexity is O of n squared. Our algorithm, the way we implemented it, also its best case complexity is O of n squared. You can make a minor improvement to this, which is also, which you find in the coursework. You would essentially optimize this for the best case, and best case means you pass a data set that is sorted already. And then actually, if you optimize it, you would avoid running into n squared. For the best case, it would be just O of n. You need to think about a trick, how to change that, or that you would know early when to abort. It's also explained in the coursework, which is problem 11.1. There's also a small hint. It's just a few lines of changes, but then your best case time complexity becomes O of n. So it's better than our implementation that I've just shown. The average case time complexity is also O of n squared. And our bubble sort has a space complexity of O of 1, which means it's in place. because it only needs constant much extra space because we have this helper variable and n, but that's it. I don't need to create more helper variables or that the number of helper variables would depend on the length of A. And that's why it's constant space complexity, which we also call in place. Then bubble sort has another property, and we say bubble sort is stable. And this is, now you're wondering what's a stable sorting algorithm. I will show you this. Stable sorting means that that stable sorting algorithms, they would sort repeated elements in the same order as they appear in the input. And what does that mean? If we just look at our bubble sort example, imagine you would have two 8s in here. For example, you would have this 8, and then somewhere else, like maybe between 4 and 6, you would have another 8. And if you then sort your data set, you would not change the relatively order of these two 8s. So when you sort with a stable sorting algorithm, that last 8 would also be the last 8 after being sorted, and the first 8 would be the first 8 after being sorted. So you would not change the relative orders or order of these elements. You're wondering, what is this useful for, or why does it matter if I have an 8 and another 8 and I change their order or I don't? For such simple data sets, arguably, it wouldn't make much of a difference. But if you could sort after multiple criteria, if you have maybe more complex data, then it does make a difference if you have actually a stable sorting algorithm or not. And there's an example in here to visualize this, but actually I have a much better example here where we can see this. Now, we have an input string, which is a tongue twister, which is something like, how much wood would woodchuck chuck if woodchuck could chuck wood? And what I'm now doing is I'm calculating the word count of this. The word how appears once, the word much appears once, wood appears twice, it would appear here and there. Wood appears once, woodchuck appears twice, chuck twice, if once, and could once. And the data I'm working on now with my sorting algorithm is not just, single integers, but it's actually tuples. So this is a tuple of a string and an integer. The next element in my data set is another tuple of a string and an integer. And what I'm now doing is I'm doing the first pass of sorting, and it's a lexicographic sorting, which means I'm sorting the strings, and I'm sorting based on the strings. So I have my tuples, and I'm sorting the tuples based on the strings in a lexicographic way. And that means chuck appears first, then could, how, if, much, would, woodchuck, would. This is lexicographic sorting. And we have now sorted these tuples based on the string. So chuck still has integer 2, how still has integer 1, and so forth. And now I want to do a second pass of sorting based on the integer. So I'm taking my data set that I have sorted with the first pass by looking at the strings. And now, based on this, I want to sort based on the integer. And if I use a stable sorting algorithm, what I notice here as the result is I'm sorting, and I'm sorting the integers in a descending way. So all the pairs where the integer is 2 appear first, and then all the pairs where the integer is 1 appear second. So it's sorted in a descending order by the integer. And if I have a stable sorting algorithm, I will first have the word chuck, then wood, and then woodchuck in this group where the integer is 2. And I see where the integer is 2 in this group, the strings or the pairs are still sorted based on the strings in a lexicographic way, and the group where the integer is 1, they are also sorted lexicographically. Could, how, if, much, would. And that's the consequence of stable, because I have what we said before. Stable sorting means repeated elements will appear eventually in the same order as they appeared in the input. And the repeated elements are now these 2s and 1s, but before Chuck was before would, and would was before woodchuck, and that order is now not changed with a stable sorting algorithm. And it's the same for all the pairs where the integer is 1, they still appear within that group of 1s, appear in the order as before. So they're still sorted lexicographically. And the second pass, if you use an unstable sorting algorithm, this order would not necessarily be maintained. So if I take the data from my first pass and I then put it in an unstable sorting algorithm and I want to sort based on the integer, obviously I have the ones with 2 first and then the ones with 1, but they are now not sorted lexicographically anymore within that group of 2s and that group of 1s. And stable sorting is, for example, essential for an end user if you, I don't know, use Microsoft Excel and you sort tables based on multiple columns. There, often you really want stable sorting because it's a key property then for you to visualize your data. Maybe it is something you have noticed when you work with Excel and you sort a table based on multiple columns. And for something like Excel, you definitely want a stable sorting algorithm. And the good news is our bubble sort is definitely stable. So that's a good property. Now, if you look at a typical introductory course to algorithms and data structures, there are 2 more algorithms that are discussed in detail. They're called selection sort and insertion sort. And a lot of professors spend a lot of time on them. And frankly speaking, I don't really know why they do this, because these 2 sorting algorithms, they are both inefficient. We'll see them in a moment. And we could be discussing them now for the next hour, but probably you will never really be using them directly because they're inefficient. And we've seen now one inefficient algorithm like a bubble sort, and I think that's enough when we look at inefficient algorithms. At the end of today's lecture, we wonder when we would actually be using a bubble sort, because there are a few reasonable use cases when you would actually be using a bubble sort, but those are extremely rare. And things like selection sort and insertion sort are probably relatively rare as well. So we will now not look into them. If you're curious about selection sort and insertion sort, look into the book or Wikipedia. They're visualized and you can look at them, but they are also both very inefficient. So I don't want to be spending time on this in this course. Just if we look at their properties, we see selection sort. Well, it has a space complexity of O of 1, but then worst case, best case, average case, time complexity is O of n squared, and it's even unstable. So it doesn't seem to offer really any advantages compared to our bubble sort. And the insertion sort, also space complexity of 1, comparable to our bubble sort and stable. So it doesn't seem to offer any real benefits. And O of n squared, by the way, is really bad as a complexity. Maybe not for 5 elements, but imagine you put in 1,000,000 elements, and then you have something in the order of 1,000,000,000,000 operations that you would be running just to sort that. So this is definitely not going to be scaling. So we need sorting algorithms that come with a much better complexity. And we will now be looking at 2 algorithms that do exactly that. One is called merge sort, and merge sort is a divide and conquer algorithm. So divide and conquer is a concept we saw before. in last week's lecture, or 2 lectures ago, where we saw if we have a problem that we are unable to solve, maybe we can break this into smaller subproblems and then solve them and then put it all together. And we saw that such divide and conquer problems can often be expressed very neatly through recursion. And merge sort does exactly that. It's a divide and conquer sorting algorithm. It works bottom up and it's super efficient. And what it does is, just from a high-level description, and then we will visualize it, we will divide an unsorted list into n sublists. And each contains only one element. And if we have a list where there's just one element in, this is actually sorted because it's just one element. And then we try to repeatedly merge these small sublists into new, larger sublists that are then sorted, because if I have 2 elements, one from one list, one from the other, I can just put them in the right order and I'm done just by merging it properly. We'll also see later how merging works. And then I keep doing this. I have then later 2 lists. Each has 2 elements which are sorted, which I just merge, and I merge them again, and I keep merging until I'm done. And then I have a sorted list. This is the idea of merge sort, and we will now be visualizing this. There are a few figures that are here from the book, and I won't be visualizing this on the iPad because it looks already super nice in the book. I have my data set, which is unsorted, and I'm unable to directly sort this. So divide and conquer. Maybe I can break this into a left list and into a right list. I try to sort them, and then I merge them. In the left list now are elements 85, 24, 63, and 45. This one is still unsorted, and I'm unable to directly sort it. So I can again break it into 2 sublists, 85 and 24, and then I still have the other sublist 63 and 45. But the 85 and 24 is still a list of 2 elements, and I said I need to break these lists into smaller lists that just have 1 element. So the left list now is 85, it's a single element, and the other one is 24. And now I have an element 85 and 24, where one sublist has the 85, the other one is a 24. These are the smallest possible sublists, and then I just merge them by picking the one that is smaller and then the one that is greater. So I'm just putting them together now, I'm merging, and I say I have a 24 and an 85. And this sublist now is sorted, because I took the sorted sublists, one has a 24 and the other one a 25, and I just merged them in a way that I again have a sorted list. So it's my 24 and 85. I still have then up here my sublist 63 and 45. 63 and 45 is not sorted, so I need to break this again down. And I have a 63 and I have a 45. So I'm again splitting this into 2 sublists. Now I have reached the smallest size possible, and then I merge them. So I first pick the 45 and then the 63. Now I have my 2 sublists. The one is here 2485, which is sorted, and the other sublist is 4563. And then I just merge them. Both sublists are sorted. So when I merge them, I'm looking at the beginning of both sublists and I pick the smaller element. Then I pick the 24. This is the first one. Then I'm picking the 45, which is the next smallest element. And then I have the 85 and the 63 left. 63 from the right sublist and then the 85. Now from my whole data set from before, the whole left is now sorted, because I started with this whole data set and I split it into a left, which I now have sorted, which is this one here. And I'm just applying the same procedure to the right sublist again. And the right sublist, I could just now go through all these steps, but I can skip it because all I have done on the left, I would just be doing on the right. And this sublist, which is 17, 31, 96, and 50, once I have applied the same procedure over and over again, I will get a 17, a 31, a 50, and a 96. This is the right sublist. I have my left sublist, and I'm now just merging them. So I'm always looking at where do I get the next smallest element from. Initially the 17, then the 24, then the 31, then the 45, then the 50, then the 63, then the 85, and then the 96. And eventually I have sorted my data set. I know this looks complex, but it turns out using recursion, we can implement something like this super easy. The key essence of this seems to be the merging. Like, how do I merge this correctly? Or how do I merge two sublists correctly? And for merging, I have one instance here just to show it to you how it works. So I have my two subsets or sublists S1 and S2, which is the 2, 5, 8, 11, 12, 14, 15. And the other sublist is also sorted. It's a 3, 9, 10, 18, 19, 22, and 25. First, I pick the 2, because the 2 comes from S1. Then I pick the 3 from S2, then the 5 from S1, then the 8 from S1, then the 9 from S2, and I see I have an index. There's an index I, which I keep moving in S1 when I have picked an element, and I have an index j, which I keep moving when I have used an element from S2. And in my result set S, I also have an index, and the next element I'm looking at is index I plus j. And for index I plus j, I need to pick the right element, either from S1 or S2. And in S1, I have the index I, which points to element 3, which has value 11. And in S2, I have index j, which refers to index 2, and I have a 10. So I picked a smaller element. That means I picked the 10, I put it in at this index. Then I move index j from this 10 to the next element. It's an 18. And then I would continue. So for index I plus j in the result set S, I would look at where does the I point to, where does the j point to, and I pick the small element. So I would pick the 11, and then I move I to this 12, and I just continue like this. So that's what merging does. And if I try to implement merging, I have three parameters. I have S1 and S2, which are the sublists, and I have S2, which I will manipulate. So I'm reading from S1 and S2, and I write into S. And internally, I need my helper variables, which are indexes I and j. Initially, both are 0, just pointing to the first elements. And then while there is still something to read from either S1 or S2, while there's still something left in them, I would keep comparing and pick always the smallest element, either from S1 or S2, and then write this into S. I will not be implementing the merging here with you, because take a look at the coursework. This is one of your tasks in the coursework, that you need to implement merging. But merge sort, you don't need to implement merge sort. This is something we're now doing together, but you need to implement this helper method, which is called merge. Then I will quickly copy and paste the merge function into my IPython. I will not show you this because then I would be revealing the secret to you, what merge looks like. So I'm just quickly, secretly copying it, and I'm clearing the screen. And now that this is done, I will share my terminal with you again. And you should be seeing the terminal now. And now we will not be implementing merging because this is your coursework and I have just copy pasted it and have cleared the screen. So I have my merge method. So we see there is something, the function is there. What it looks like is my secret. You need to implement this in the coursework, but we will now implement merge sort, and we are passing S and we are manipulating S. And we're not returning S, we're directly manipulating S. So we're passing a reference to our data and manipulating it. And we need to know how many elements are in S. And if there are less than 2 elements, I'm done. Because if there are 0 elements in S, there are no elements to be sorted. And if there is a single element, then my data is sorted already. Now it will become more complex. I need to calculate the middle index. And for this, I'm doing an integer division. So I divide n by 2. And remember, in Python, if I divide an integer by another integer, the result is a float. So 5 divided by 2 is a 2.5 in Python 3. So I need an integer division, which is written in Python this way, but we've seen this already before in this course. For example, in binary search, where we needed the middle index. And now what I want is, I want to take my data from S that goes up to the middle, where the middle index is excluded. So with this slice, you need to imagine it's like starting index 0 up to the middle index, where middle index is not part of it. But if I leave the 0 out, it's just like this. It's the same. I don't need to write the 0. It's implicitly in. So I have my left data set, S1, which is the left half. And I'm taking the right half, where I say from middle up to n. But if I leave the n out, it's also put in. So it's implicitly from the middle element, where middle is included, up to the last element. So I have now split my data set into left and right. And then we said before in our visualization, well, I'm doing a merge sort on the left. I'm doing a merge sort on the right recursively. And once this is finished, I get something back where S1 is sorted. I will get something back where S2, the right, is sorted. And then all I need to do is I need to merge S1 and S2 into S. How to implement the merge is your homework, and then I'm done. So I'm applying divide and conquer. I'm unable to sort the left and the right directly, so let's again break it further down, divide and conquer. Eventually it will be finished, and then I have the sorted left, I have the sorted right, and then I just need to merge them and I'm done. And it works recursively, and it will eventually, the recursion will stop when I just have a single element left or a no element in a sublist. Imagine it could happen that maybe an empty list is passed, or maybe the left or right has an odd number of elements. Then it could happen that I have a sublist with 0 elements, but this will always then terminate the recursion. And then I'm just combining those subproblems that are sorted. And at the end, or in order to combine these sorted subproblems, I'm doing merging. And we can now see that it actually works. So I have a data set we just used the data set from before that I had put in the slides. So it's 85, 24, 63, 45, 17, 31, 96, and 50. And now let's do a merge sort of the data. And we see the data is now perfectly sorted. It's 17, 24, 31, 45, 50, 63, 85, and 96. This is the implementation of merge sort. And now you're wondering, what is all of this useful for? It turns out that merge sort has a worst case time complexity of O of n log n. Why is that the case? Remember from like 2 weeks ago when we started with recursion, we looked at recurrence relations. And the recurrence relation for merge sort would be that T of n is 2 times T of n half plus something for combining. And there's something you can think about what the term for combining here, in this case, merging would be, or you just go back a few slides where I had this table of recurrence relations. And there you find the recurrence relation for that describes the behavior of merge sort. And then you know how to solve a recurrence relation, either manually or you would be using the master theorem, which you can use for that kind of recurrence relation. And then you'll know the worst case time complexity is O of n log n. The O you would get if you manually solve the recurrence relation. If you use the master theorem, you would even get a theta. It also turns out that the best case and average case time complexity is O of n log n. So the best case here means even if you put in a sorted data set, it would still take n log n much time because the algorithm doesn't check beforehand if your data set is sorted. You could be doing that. You could try to amend it and, for example, first go through the data set and check if it's sorted, which takes O of n, and then maybe abort from there. So you could improve the best case time complexity very easily. One good advantage of merge sort is it is stable. The space complexity of merge sort is O of n because we have all these recursions in there, and recursions plus these helpers for splitting the data into left and right, all of this consumes memory. And that's why the space complexity is O of n. So it needs far more space than, for example, our bubble sort. But O of n log n is far better than n squared, which is the worst case time complexity of bubble sort. And then when you make n super big, obviously this one here will run just a little bit worse than linear, and far, far better than O of n squared, which is the complexity of our bubble sort. But take a look at the recurrence relation and try to solve it. Again, this could be some practice for you. We've discussed recurrence relations a lot, and they are definitely super important to this course. So that's merge sort, and overall, a massive improvement compared to bubble sort for the worst case. Now, we said that our merge sort works bottom up. It's a divide and conquer sorting algorithm that works bottom up. And when we discussed divide and conquer, we saw there's not just bottom up. You can also interpret it from the opposite direction, which is top down. And there is another super efficient sorting algorithm, which is called quicksort. It's again a divide and conquer algorithm, but this time it works top down. And quicksort works quite different to merge sort, and later we'll also compare their complexity. And what quicksort does is it looks at the data set, and there is a pivot element. So it looks at the unsorted data set and it takes that pivot element from the list, and then it goes through the list, and all elements that are smaller than the pivot will be put into the first sublist, and all elements that are the pivot or greater than the pivot, you would put into the right list. And you need to think maybe about where to put the elements that are equal to the pivot. You can put them either left or right. You just need to do this consistently, obviously. And then you have your sublists. So in the left sublist, you have everything that is less than or equal to the pivot element. And in the right sublist, you put everything that is greater than the pivot element. And then again, recursively, you would sort them further and so forth. And you would just apply the same procedure over and over again, top down, and eventually you have sorted your data set. And we'll be looking at this now. And what we see here is we have our data set, like the one from before, 85, 24, 63, 45, 17, 31, 96, and 50. And there is an element that is highlighted in bold. This is the pivot. And remember, everything that is less than or equal to the pivot, we put into the left, and everything that is greater than the pivot in the right. So we will then take our element 24, the 45, and the 17, and the 31. They are less than the pivot, so we put them in the left sublist. And everything that is greater than the pivot, we put into the right sublist. So 85, 63, and 96. The pivot we don't care about right now. The pivot will be used later when we combine. And then this sublist here, we again need a pivot. And our convention right now in this visualization is here, the pivot is always the rightmost element. You could also pick the leftmost element. So you could also have picked here the 85. Here we pick the rightmost element. And in this sublist, again, we pick the rightmost element. It's the 31. And we split into left and right. So 24 and 17 are less than the pivot. And our 45 is greater than the pivot. And we can again split this subset into our 24, which is greater than the pivot. The pivot is 17, and there is nothing less than the pivot, so the left sublist is empty. And eventually, we will now put all of this back together. For the left sublist, we take the left, for this one here that we wanted to sort, we pick the left sublist, which is empty, then the pivot, which is 17, and then the right sublist, which is 24. So now I have this small sublist sorted. And this one here, I can sort by taking the left sublist, 17 and 24, then the pivot, and then the right sublist. And the pivot was the 31, and the 45 is the right one, and so forth. And I need to apply the same procedure to the right sublist from the beginning, 85, 63, and 96. 96 is the pivot, and I break this sublist into a left, or this sublist here into a left one, which is 85 and 63, and the pivot and the right sublist. Eventually, I apply the same procedure over and over again. So the sorted right list is then the sorted left list, or left sublist, which is 63, 85, plus the pivot, plus the right one, but the right one is empty. So now the right sublist is sorted, 63, 85, 96. And eventually I take this left sublist, which is then here. I take the pivot and the right sublist, because the right sublist was always meant to have elements that are greater than the pivot. And I'm done. So this is a visualization of quicksort. And we will also try to implement quicksort now. And I will show you this interactively, it looks more complex than it actually is. So this is our data set. And we will now implement quicksort on S. And we will check if the length of S is less than 2 or less than or equal to 1. And so as before, you can also put a less than 2 or less than or equal to 1. That means if there is 0 or 1 element in S, we're aborting. Now I want a left sublist of my S. I want a right sublist of S. And I want my pivot element. And in this implementation, I simply say I'm picking the leftmost element as the pivot, but you can pick the leftmost or the rightmost element. That's your choice. And then I want to go through all elements in S, and I check if the element that I'm looking at is greater than or equal to the pivot. And if this is the case, then I'm appending the element to the right, because an element that I just found is greater than or equal to the pivot. So it's something that I put into the right sublist. Otherwise, I'm putting this element into the left sublist. Now I have my left and right sublist, and I'm unable to handle them or sort them directly. So I'm doing divide and conquer. I'm applying quicksort to the left. And what I get back, I assign again to the left sublist. Now I'm applying quicksort to the right in order to do the same. But here I need to make one minor change. And I need to say, I take all the elements from the right, starting the first element or starting index 1. So I'm skipping index 0. Why am I doing this? Because here I said I'm picking the pivot, which is the index 0, and I'm checking then all elements in S, and I'm checking if an element is greater than or equal to the pivot. So the first element in S is actually the pivot element because I picked it here. And I don't want to process the pivot further. And that's why I'm not putting in all the indexes starting 0, but starting 1, because index 0 is the pivot element, and I don't want to process this further. You could also write this loop in a different way, or you could somehow skip index 0 in here, but I'm just skipping it here. Then we will see quicksort is returning something for the left, and for the left, it's actually returning the sorted left, and for the right, it's returning the sorted right. And now I have my lists left and right, so I'm just combining them. So I'm just appending the right list to the left list, and I can return this. But there's actually one more thing I need to do. I have my pivot element. I also need to put this in, but the pivot is a single element. It needs to be a list that this syntax works. And I'm saying I'm taking the left list. I'm appending then the pivot element, which is in a list. And then I'm appending the right list. And I'm returning this. And let's see what it does. The quicksort is called on the data, and it actually returns a sorted list 17, 24, 31, 45, 50, 63, 85, and 96. So we see on our example data set that it works. And again, we can implement it super easy because it's just divide and conquer. So we can here really take advantage of recursion. For the complexity, it gets more tricky. if you look at a standard quicksort, let's maybe start with this. A standard quicksort is unstable. But there are lots of variations of quicksort. We've probably just looked at the most simple quicksort possible. There are stable implementations of quicksort. The space complexity of quicksort is O of log n, but that's better than our simple implementation here. Our simple implementation is terrible in terms of the space. It isn't that great, but it's just probably the most simple implementation one could take. There are better ones. And then we see the best case and average case time complexity of our quicksort is O of n log n. And for most data sets, you would put in there, quicksort would run in O of n log n. Unfortunately, there is a worst case for which quicksort takes O of n squared. Do you have any guess what kind of data set for quicksort could be the worst case? And you can turn on your microphone and share your insights, or maybe send this here in the chat. For what kind of data we may run into O of n squared? And this is right, what we got in the chat. If the pivot is the smallest or greatest element in the data set. So here, the pivot, we picked the rightmost element, and we were somehow able to split this then into a left and right, because the 50 somehow splits this, or approximately, into two halves that are equal size, more or less. However, if I pick the 96 as a pivot, then all the remaining elements would go into the left. And if this happens again in the left, that everything goes into left and right except the pivot, then this will definitely not run in O of n log n. It will actually take O of n squared. And when can it happen that maybe the left or rightmost element as the pivot creates such a situation? Well, if I put in a sorted data set first. If I put in a sorted data set, then if I pick the leftmost or rightmost element as a pivot, I will always create this situation where I'm unable to really split this into a reasonable left and right, but it will actually not work the way I expect it to work, and my quicksort will then run in O of n squared. That's not great. So we could maybe say we are checking if our data set is sorted beforehand, and if so, we're just done. That's one approach, but maybe our strategy for picking a pivot is still bad, because even if I put in a data set that is almost sorted, the quicksort could run terribly slow if I pick my pivot like this. And that's why there is another problem, and there's a check question here. If the list is already sorted, does it always have this worst time complexity? Yes, if your data set is sorted already and you pick the pivot as the left or rightmost element, then this will definitely take O of n squared. So we said we could check beforehand if the data is sorted, but say if it's almost sorted, then you would still run into O of n squared, because you could maybe rule out the case where it's totally sorted and say it's totally sorted, I don't need to sort, this takes O of n. But if it's almost sorted, then you would still run into this problem of O of n squared. And that's why there is some coursework problem where you could think about a so-called randomized quicksort, where you would randomly pick the pivot element. So in your data set, you would just randomly pick one. You can try to implement this, and you can wonder about its complexity. So there is some coursework in here, which is problem 11.3. And it turns out, even for a randomized quicksort, In the absolute worst case, this would still be O of n squared, because you may be just extremely unlucky in how you're picking your pivot, and you're always picking the worst pivot possible. But this is super unlikely, but still it could happen. So it's still O of n squared, but probably super unlikely. And this is explained here in the coursework with some text. Also with a link where some explanation of this comes from. There's a course at Princeton where there was some of this argued, and take a look at it. So why is quicksort called quicksort? Because in practice, and this was noticed many decades ago, from all these fast ones like merge sort, quicksort still tends to run somewhat faster than, for example, merge sort in real world problems. Not better in terms of the complexity, but in terms of the operations it needs in the time, the concrete running time when you run it. And that's why quicksort has become so popular, and it's called quicksort. And this worst case is extremely rare, yet it could still happen, but even with a randomized quicksort, but it's super unlikely. Now I need to say we have implemented these algorithms probably in the most simple way possible. If you take professional implementations of quicksort, merge sort, they are implemented in a much more elaborated way that works better and needs less resources. But this is something that would be like an advanced course in algorithms and data structures where you would look into this. But probably you will not be implementing quicksort or merge sort from scratch anyway, because you would just be using a library where this is implemented. And when you check the literature, you would see there are many variations of quicksort, merge sort, and so forth. Lots of them. And there is also a sorting algorithm that is popular that is called heap sort. Heap sort is pretty interesting from a theoretical perspective, because its best or worst, best, and average case complexity is O of n log n, and it's O of 1 memory. So it's actually an in-place sorting algorithm, but it's unstable. And in practice, it performs slower than a well-tuned quicksort or merge sort. So from a theoretical perspective, it's cool, and it comes with O of 1 memory because it does some special tricks with the memory to enable you that you only need constant much extra memory. But in practice, it is slower than a well-tuned quicksort or merge sort. And quicksort is unstable, but there are also, again, variations of quicksort that are, for example, stable. Then there is another algorithm that is called bogosort. When I asked you for comments on sorting algorithms you have come across before, some of you also wrote bogosort. Bogosort, it's more like an illusion. It's a joke, because what bogosort does is you take a data set, you randomly shuffle it, and you check if just by chance it is sorted. And if so, you would then return it as sorted. If it's not sorted, you would then shuffle again and check again if it's sorted. While this may come to an end at some point for a small data set, for a large data set, it's just super unlikely that it will ever in your lifetime be sorted just by randomly shuffling it. So this is more like, more like a joke. It's nothing concrete. And there's a question if there are real-world applications for such choke algorithms. Well, at the end of this course, we'll be looking at quantum computing, and there is more like this choke of a quantum bogosort. You will see this when we look into the concept of quantum computing and superposition. This could be an application of quantum computing, in fact, but that this ever really works for a quantum bogosort, I'm not sure. You would need a quantum computer, or not happen in the foreseeable future, because you would need a quantum computer with lots of quantum bits. that this is anywhere near to working, so I don't know. For now, probably bogus sort is more like an illusion, at least with classical computing. Now, there was a very funny video from something like 2007, 2008, when Obama was aiming to become the Democratic nominee for the US election. And he visited lots of companies for, promoting his campaign. And Obama also was invited for an interview at Google. And Eric Schmidt, who was the chairman of Google at that time, he argued that getting a job at Google was more difficult than becoming president. And he interviewed Obama on various things. And he actually asked Obama also a question about sorting algorithms. And if you're curious about Obama's answer, which sorting algorithm he would pick, take a look at the video. So this was something that was quite popular in 2007, 2008 in the computer science community. Now, we have seen now merge sort that works in O of n log n, quicksort probably as well in most cases, heap sort and so forth. And we can wonder, is there a sorting algorithm that works better than O of n log n? And all these sorting algorithms we have looked at today, they are based on comparisons. We compare two elements, which one is smaller than the other one. And it can actually be proven that for sorting algorithms that are based on comparisons, omega of n log n is the case. So this is the lower boundary. So n log n is the lower boundary for comparison-based sorting algorithms for the worst case input. So for the worst case input, it's impossible for you to be better than n log n if you use comparisons. So there is no O of n sorting algorithm that uses comparisons. But there are other approaches to sorting. For example, there is a bucket sort. So you have your data set and you distribute the elements of the array into a number of buckets. And if you have k many buckets, and you say k is equal to n, so you have as many buckets as input elements, and you assume that your data set is distributed uniformly, and given some other specific circumstances, such a bucket sort can be O of n, but it comes with more consequences because you need all these buckets. Something that is probably, again, not that reasonable in practice. And in practice, most sorting algorithms are comparison-based, and they work extremely well, like quicksort and merge sort for real-world data sets. But those ones that are based on comparisons, they cannot be better than n log n for the worst case input. Obviously, for the best case input, O of n, we've seen this, but for the worst case, and that's what we care about. Now, we've seen these algorithms, and the bubble sort really looks like a bad choice because the bubble sort looks super inefficient. And you're wondering, why did I actually discuss the bubble sort in the first place? The good thing about a bubble sort is it's very easy to explain. And you see very quickly that it's inefficient. And then you think, well, bubble sort would never be used in practice. It turns out there are some use cases where bubble sort actually makes quite sense. For example, if you have a data set that is maybe already almost sorted, and you just want to continue in almost sorting it. So you maybe don't care about that the data set is not fully sorted at the end, but you don't just want to do a few iterations of the outer loop in your bubble sort, and you don't want to finish when it's fully sorted, but you just run a few iterations of the outer loop, and you just want to continue the sorting, but you don't aim for it to be fully sorted. And there are applications for this, for example, in game programming, especially in graphics, where you maybe keep a list or a spatial list of objects, for example, pixels or other objects, and you just want to, until the next frame, you would just want to sort them a little bit further, and then you want to visualize the frame. So if this list doesn't change too much between frames, maybe you don't need it fully sorted for the next frame, but you just want to have it almost sorted for the next frame. And then this frame is there for a few milliseconds, and then you have the next frame. So maybe it doesn't matter if your data is not fully sorted in this graphics visualization in every frame, but as long as it's almost sorted. And something like this is used in game programming and graphics. And for this, actually, a bubble sort turns out to be extremely helpful, where a quicksort or merge sort would not be helpful at all, because you have limited time between your frames, because you want to render your graphics without any interruptions. And here, a quicksort or merge sort may lead to interruptions, but with your just a few passes of the bubble sort, or maybe just do one pass of the outer loop, you would actually be able to keep this almost sorted. And this is something that was discussed in a Quora article some years ago, and I thought this sounded quite reasonable. And then I checked with one of my contacts who worked in graphics at Apple in the past, and he said this is exactly what they did in his software that he worked on as well. So this is not made up in this Quora article. It's actually being used by graphics experts. But nonetheless, I think the number of real-world use cases of bubble sort is probably quite limited, but there are still some use cases. In practice, you would be using a quicksort, a merge sort, or something like this, and probably you'll be perfectly fine for 99% of all your problems. We'll also be seeing in future lectures data structures that keep our data sorted when you put it in. So they use a slightly different mechanism. And we will also compare the complexity of all of this to each other. But you've seen that overall sorting can be done quite efficiently. And we need sorted data in order to efficiently then work on the data or to manipulate it. Now you're wondering which sorting algorithm is implemented in Python, because in Python there is the sorted function which does sorting. We'll try this out in a moment. And in Python, there is actually, it has its own sorting algorithm, which is called timsort. And timsort is a stable sorting algorithm, which is actually a combination of merge sort and insertion sort. And this one is designed to perform well on many kinds of real-world data in the Python environment. And this was proposed by Tim Peters in 2002. And this is the one you get now with the Python implementation. It's stable, which is good. Stable is important. We need space complexity, that is O of n here for our timsort. And the worst case and average case is O of n log n. And for the best case, meaning I have a sorted data set already, it's O of n. You can check the Python documentation if you're curious about timsort, but for now, maybe just use it. And I'll show you now in the next section of how you can actually sort data in Python. So we have our data from before, and you can just call sorted. So sorted, as you see, is a function that comes with Python, and we pass a so-called iterable, which is a sequence or something that you can iterate on, and it will return you this in a sorted way. It has a couple of parameters that we will explore very soon, and we can call sorted on our data, and we get our sorted data back. So this is super easy in Python, and it runs super fast. It's this tim sort, but with all sorts of extensions that it's also faster by probably a certain factor, in addition to this good complexity. But feel free to implement your own quicksort, your own merge sort, and compare this to sorted for a sufficiently large data set. And then you can measure the time with time, for example, as you remember, and you can see what happens. Before, we've looked at these tuples, which have two entries, like a string and an integer, and we have sorted them by one and then the other criteria. I also briefly want to show you how you can do this in Python. In Python, there is the operator package, and we need the item getter function from there. And we now build our new data set, which is a list, and the list contains tuples. So for example, the first one here is a tuple with the string red and the integer 1. Then the next one is the string blue with a 1. Then red with integer 2. And again, a blue with integer 2. And if I now want to sort this data, I also somehow need to specify a criteria by which of these entries do I want to sort a list of tuples. And I see there is a key parameter, which is optional. And I can say, well, I'm using the item getter, and item getter 1 means I'm using the index 1 within the element. So I have these tuples, and index 1 would be the second element, the integer, because index 0 would be the string. And I say, well, I want to sort based on the integer. And then this is what I get back. I first get the integers 1, those tuples, and then the tuples with integer 2. I sort this in an ascending way, starting with 1s, then the 2s, but I can also reverse this, and I can just reverse the order, and I have something like this then. Well, reverse the order. Now I'll reverse the order, and the reversed order is now starting with the 2s and then the 1s. You can obviously also use the index 0 to sort this based on the string, whatever. So if you have multivariate data and you need to sort multivariate data, this key is one way how you can do this very easily in Python. And the sorted function is implemented efficiently, but feel free to measure this on your own and see how its running time compares on your data compared to our own quicksort or bubble sort implementation. And I've talked about the coursework. So problem 11.1 is an improvement of the best case running time complexity of our bubble sort. Then implement the merge helper function for merge sort, as well as work on a randomized quicksort. And if you do this, this will give you some extra experience in sorting algorithms. I've mentioned briefly the recurrence relation for merge sort. The recurrence relation for quicksort is also something you can be thinking about. And then you can solve these recurrence relations, or I'll briefly show you those recurrence relations that we are all on the same page. So for merge sort, this is the recurrence relation because I'm splitting my data set into left and right. So 2 times n½ plus n for merging these two halves together. And I see the complexity is O of n log n. You can either solve this manually or use the master theorem. Just going back. And this is what we have just done. And we have now finished sorting. And if there are any questions, maybe just ping me now in the chat briefly. Otherwise, we are done for today. I had sent the link for the course evaluation in iLearn, and so far I have not received a lot of course evaluations yet. However, I would appreciate your course evaluation, and I will briefly share the link here again in the chat so you can take advantage of the course evaluation. I'm sharing it in a second here in the chat. And you can open the URL and evaluate my course. And next week, I hope to see you in the lab. Today, the lab was quite empty, so I hope to see more of you next week, because the lab is an opportunity to discuss all of these problems with me if you attempt them or you have problems with them. And next week, we'll be looking into trees, which is another fundamental structure. And trees allow us to organize data in a sorted way. And in order to work on trees, knowing recursion is very helpful, because trees are an inherently recursive data structure. And that's why we did recursion first, and then sorting, and then trees, because both heavily rely on recursion. And I look forward to seeing you next week. Enjoy the weekend and take care. Goodbye.